All right, welcome to CS4510. This is what, L04A. The topic of today is context free grammars. Okay, so there's two or three words in what the topic is. First is context free, and the second is grammars. What does context free? Context free is the description of what the kind of grammar is. We'll have to talk about why it's context free later. In fact, next time. But today we're just going to talk about grammars in general, and then specifically the context free grammars. So what's really a grammar? The difference between a grammar and an automaton. An automaton is, as we've defined in a DFA or an NFA or something analogous to this, a GNFA, and it's tasked with decision, right? Or recognition. What does that mean? On input a word, the automaton has two lights and it says yes or no, right? In contrast, a grammar does not have an input or output. It somehow is tasked with production, right? So it just non-deterministically, perhaps, just describes or produces all the correct strings and none of the incorrect ones. That's what a grammar does. In some sense, it's a string writing system, and today we'll spend the whole day on such examples. But there's already a kind of an immediate difference in comparing what these can or can't do. So for the first one, in automata, determining the question, is W an element, is W accepted by a DFA? This is a very easy problem to do on a DFA, right? You just give the DFA the word and it says yes or no. Kind of easy. But then characterizing the entire set of accepted strings is a little harder. Not necessarily hard, but like, what is all the accepted strings? And again, the language of an automata is the set of strings that it accepts and none of the strings it rejects, right? So this is all the strings that bring it to accept. So you can determine easily if one string accepts, but how do you characterize or define all possible strings that would bring it to an accepting state? That can be sometimes a little more difficult. And a grammar, on the other hand, has the opposite problem. Determining if a single word is produced by a grammar, it's not necessarily hard, but it can be harder to determine if a single string is ever produced by such a string writing system. But then it turns out characterizing, and this should be a G here for the grammar, characterizing all of the strings is actually, I think, easier. So it's a totally different system. In some sense, not really under the definition, but a regular expression is a kind of, it's not a grammar, but it's difficult to determine if a single string is described by a regular expression, but then characterizing all these strings that a regular expression describes is pretty easy when you look at the regular expression, right? That's kind of the difference here between the two. And the rest of today is going to be just spent on what are context-free grammars, right? So questions on that so far? Hopefully none yet. So what's a context-free grammar? It has four parts, V, sigma, P, and S. V is a set of non-terminals. So for example, V could be SAV, right? It's finite, it's non-empty, and we usually denote non-terminals as capital letters. Sigma is our alphabet, but in the spirit of formal language theory, we call it terminals. This is usually going to be a lowercase. That's the way we'll distinguish a terminal from a non-terminal. P is a set of productions, or rules. What is a production? A production is of the form, it's got a left side and a right side. It has a single non-terminal on the left side, then there is an arrow, and then there is a possible string of terminals and non-terminals on the right side. So when we say V union sigma star, what we mean is some sequence of terminals and non-terminals. So on the left side is a single non-terminal, and on the right side is a sequence of terminals and non-terminals. For example, it could be A goes to lowercase b, c, e, f, g, h, something like that, right? anything could go there. And in fact, because it's sigma star, it could even be the empty string. And then S is just the designated start. Like everything, we have to start somewhere. And S is, of course, an element of V. So these are the 4 parts of a context-free grammar. Just like with the automata, you have the formal definition of Q, sigma, Q0, delta, and F, and then you have the actual examples where you actually like see what it is, right? When we draw the automata, we don't really give like the lookup table for the transition function and all these other things. What we do is we just like draw the diagram. The same thing is going to be here. All you need to do to give a context-free grammar is going to give the productions, and then it's going to implicitly give the other stuff. These are going to be lowercase, these are going to be uppercase. S is always going to be the start non-terminal, the same way Q0 is always the start state. Let's just do, well, how does a context-free grammar produce a word? Like, what does it mean for a computation to appear? So what happens is we begin with the start non-terminal. And then we apply a sequence of productions. Let's call this U1, U2, to, let's say, UK, which then will go to somewhere W. So each of these is a sequence of productions, where, for example, if UI is equal to, let's say, UAV, where UI, UAV are all perhaps some combination of terminals and non-terminals, and we have a production of the form, let's say, capital A goes to, I'm running out of letters already, R, okay, then we take this string, we replace the terminal, we replace the non-terminal with the application of the production. So that means UI plus 1 has the option to be URV, where R perhaps could be some sequence of productions, right? So what happens here is we call U1, U2, and so on. These are called working strings, where they contain some combinations of terminals and non-terminals. And we repeatedly apply productions until we get W. And W is in sigma star. It's not a working string. It is our termination condition, right? Notice that we have to repeatedly apply productions until we have no more non-terminals in our working string. And what that basically means is we only have terminals. So non-terminals means you're not done with computation. Terminals means you're terminated, you're done, right? So we repeatedly apply productions until we have a string of only terminals, because those are what we want to produce. That's how computation works. Everything else is just intermediate in that sense, right? The working string can contain non-terminals because it means we have not simply completed. This is how computation is done in a context-free grammar. We can even write, we would say that W is produced by such a grammar if and only if from the start non-terminal you may apply a sequence of productions, and we put a star over this arrow here to mean 0 or more productions, and then from the start non-terminal you may produce W. That's the definition of computation, right? It's not a string rewriting system in some sense, because you can't really like erase anything. It is just a string writing system. So, all right, let's jump. Any questions on this definition of computation? Let's jump right into an example. Suppose I gave you the sequence of productions. S is going to go to A, S, B, and then I said S is going to go to the empty string. 2 productions here, okay? Let's just write out the parts. V is going to be just the set containing S. Sigma is going to be the set containing A comma B. Our productions are going to be 2 elements. It's going to be S goes to A, S, B, and then S goes to the empty string. And then S is just S, of course, right? What do you think the language of such a grammar is? Actually, let's rewind. Let's just throw some productions in there and see what happens, right? So let's say we have to begin somewhere. So we begin with S. Choose one of these productions, the top one or the bottom.
Top one.
So we're going to replace this S with the right side of the production. Choose one of these productions, the top one or the bottom.
Top.
Yeah, let's not do the bottom yet. So what happens here, I'm going to replace only this S. The remaining is going to stay the same. I'm drawing some parentheses out around there, but know that they're not part of the production. Notice how I replaced the literal capital S with a literal substring replacement of what the production was supposed to be, right? Let's do one more. Let's do the top one. Okay, I'm bored. Let's do the bottom one. When you have a rule of the form, a non-terminal goes to the empty string, essentially what that means is you delete the non-terminal. Imagine you inserted the empty string there. Obviously, concatenate things around, it's going to be fine, right? So we can say for certain that S, after a certain number of steps, we can in fact even count them, produces A3, B3, right? So if you had to guess, what are the strings produced by this grammar? Yeah.
Strings that start with A's and end with B's in the same amount.
Yeah. It's the classic language that we proved to be non-regular. A to the n, B to the n. Just that n is a natural number. So first off, that's a non-regular language. So we were able to give a context-free grammar to a non-regular language. So first off, we're not going to be able to prove that the context-free grammars are equivalent to the regular languages. So already we have something different. How different, we'll have to see later, but certainly it's not identical, unlike the fact that we did NFAs and those happen to be equal, and then we did regular expressions and those happen to be equal, GNFAs and those happen to be equal. We have a different thing now. So how different, we'll see, but certainly they're not the same. This is an example of a sequence of productions and also of a specific context-free grammar. Questions so far? Okay. So the rest of today is just going to be 10,000 examples. All right, suppose I asked you for a grammar of the form for WWR, which is even length palindromes, just that W is in sigma star. Describe to me, and this is a difficult question, we've only done one example, but describe to me a grammar that could produce palindromes. We gotta start somewhere, so let's go ahead and begin with S.
What's the alphabet?
Let's say AB. Good question.
So would it be S go to A, S, A, B, S, B?
Yes. Now, instead of doing something like this, and then I keep writing things, what we can do is introduce a shorthand. We put a bar here, and then we write it here. Saves us space. Now, note that those are two distinct productions. We're not done, though. We have one more thing to do. Yeah?
Empty string?
Yes. The empty string is a palindrome. In fact, it's an even length palindrome. Is it the same? Is it even length? Yeah. Is it the same as its reversal? Yeah. So it's actually an even length palindrome. This does produce all even length strings, right? Let's give an example. Let's apply the first one, the second one, the first one. So we'll go S, we'll go to ASA, which will go to, we'll replace this S with this one, BSB, A, right? That was replaced with that. And then we'll do one more. We'll do ABAS, ABA. And then that will replace with the empty string. All right. We're out of non-terminals. It's terminated. It's done. We can't produce any further. Pop quiz. Grammars, context-free grammars, deterministic or non-deterministic? Yes.
Deterministic.
Why?
Because you never know how many times it's gonna produce.
You could know the number of times, and we'll prove that later. You may know the number of times. For example, if a rule has exactly 2 symbols, and you know the length of the string, perhaps you could say something about how many productions are required, and something like this. We'll talk about that later, but there's another reason they're non-deterministic.
You can't determine the final word from just those other 2, or?
That's pretty close. I guess the answer I'm looking for is you have a choice. Non-determinism is about choice. So here, which one do you choose? That's you non-deterministically choose a production. Here I went from here to here by choosing a production. But note that that's not the only production I could have chosen, right? I could have gone from ASA to AASAA, right? So here there's an alternate path I could have done of AASAA, right? So the sequence of productions is done non-deterministically, right? Another thing to note about the difference between automata and grammars is that automata go left to right. But what's the order of a grammar? It usually goes inside out. So it's a very different kind of thing, because normally you write algorithms. You are used to reading things, making decisions, and then writing things perhaps. Here, you don't do any of that. You just you're not necessarily reading the string in any order, but it somehow has to correctly and exactly produce only the right strings, but from the inside out. So it doesn't read left to right and make a decision. It just has to, like a flower blooming, somehow accidentally create the right strings and none of the wrong strings. So notice that this grammar does not only produce all the strings in this language, but it doesn't produce any of the strings not in this language. There's no way to accidentally produce a string that's not an even-length palindrome. Right? So, questions? All right, suppose I ask you for W sigma W R, which is odd-length palindromes. Yeah.
Would you need another non-terminal?
You could do it with another non-terminal, like with DFAs, there's many ways to write the same program. I claim you can do it with still a single non-terminal.
Just use the same thing but allow A and B, right?
Yes, not simply allow A and B, but we want to restrict even-length strings. So right now, we only produce even-length strings, right? Were we to put epsilon there, we could still produce an even-length palindrome. We want to force ourselves to produce an odd-length palindrome. So in order to terminate, the grammar will have to choose an odd-length string has a middle character. We're going to force the grammar to choose a middle character. One of those must be chosen in order to terminate. So notice, first off, this grammar does not choose the empty string. This grammar does not produce the empty string. It also does not produce an even-length string. Why? These are going to be multiples of 2, and it's going to be forced to choose one of these to terminate. So this is going to produce odd-length palindromes. Now what if I wanted any palindrome? There's actually 2 ways I think you can do this one.
Combine the even and odd length palindrome terminals.
How so?
ASA, BSB, A, B, and empty string.
And again, this corresponds to non-deterministic choices. If you choose one of these 2, you are non-deterministically choosing your palindrome to be odd. You choose this one, you're non-deterministically choosing your palindrome to be even, right? So again, it can either be A or be even length, right? There either is no middle character or it's an A or a B. Okay, give me a context-free grammar for A star.
S to just A, or
Almost,
the empty string.
A or the empty string, but that'll produce the set, if we do this, that'll produce the set, it does not produce, for example, AA.
AS.
Yes. Why does that work? S goes to, let's say, AS, which goes to AAS, and eventually you get A to the NS, which goes to A to the N for any N, right? In fact, the number of times you apply that first production is the number of A's you'll produce. So this is 0 or more A's. Right? All right, suppose I had a grammar of the form S goes to AS. There's no empty string. What is the language of this grammar?
Undefined, since it never actually completes.
Almost. You're kind of right. Like, S goes to AS, and then what? We have one production. S goes to AS, and then S goes to, AAS. AAAS, right? But we never get rid of that non-terminal. But it's not exactly undefined.
Empty set?
The language of the grammar is said to be the strings that are produced by this grammar. Now, you could think of it as this grammar gets stuck in an infinite loop. It doesn't really. It just doesn't, it fails to produce a, it does not get stuck in an infinite loop, it just fails to produce a string. So, no sequence of non-deterministic choices or anything like this will ever lead you to an accepting state, right? All right, give me a grammar for sigma star.
Is the language A's and B's?
Yeah, let's suppose. In general, if I don't specify, let's just assume it's A's and B's. Well, let's begin with S goes to,
Goes to A or B or the empty set.
but then what about AA?
Oh, AS, BS.
Yes. In general, by the way, same thing with DFAs. You need some sort of recursion in order to describe something infinite. So a DFA should contain a loop if it wants to describe something infinite. And same thing here, there should appear on the right-hand side other non-terminals, perhaps that go back to the first non-terminal or some combination, some kind of cycle in some way, right? Now that does produce sigma star, right? And in fact, your word is the applications of production. So let's say you wanted to produce A, B, A, A. You would do this one, and then this one in that order, right? This production, this production, this production, this production, then that one. That'll produce to you sigma star. It's not the only grammar though. Grammars are not unique. Is there a second grammar you can think of?
S goes to SA?
Yeah, that's another one.
SE, or empty string?
The grammar need not be left to right. Have the grammar produce the word right to left. Okay? There's a third one. Yes?
Since it's non-determinist, could it be S go to A, B, S, and empty?
ABS?
A or B or S?
Not quite. That'll produce, let's see what happens.
Oh yeah, that's
Yes.
sticky, yeah.
It won't write it ever. When you have a conjunction of when you have a non-terminal next to a terminal, then you know that your working string is getting longer, but here in the production it's just gonna immediately just be, this will only produce what language?
A or B.
Yeah. This is a finite language.
I see.
Yes. Give me another context-free grammar for sigma star.
We enumerate more of A and B. Could it be something like AAS, ABS? Right, and then B, enumerate all that, and then, add the single ones.
We're missing one string.
And then exactly.
So this is the same grammar, this is not the same grammar, excuse me, but it produces the same language. But instead it does the productions in a different, it chooses differently. Here it's choosing to break the string up into pairs, and then it says, produce them 2 at a time. And then produce your last character if it's odd, or if it's not odd, then don't produce any odd last character, right? The one that does not get paired. So this is another way to produce the grammar. In fact, you could even do ASA, or ASB, or BSA, or BSB, right? Or A or B or empty string. What's really the difference between this grammar and the one for palindromes? We have these rules here, these productions, right? So in some sense, when you don't have those productions, when you produce the language for palindromes, even palindromes maybe even, that you make sure that every A on the left has an A on the right. So that's what these 2 rules enforce. But these rules enforce like the opposite. They like relax that in some sense. That if you could have a B on the left and an A on the right, or, oh, it's not that one, right? Or an A on the left and a B on the right, so on. So, infinitely many such grammars for the same language. You could come up with paired 3s, 4s, and 5s in a row. Right. Questions on this one? All right, I'm going to give you a context-free grammar, and I want you to tell me what it produces. This one is a tough one. S goes to A, S, B, or SS, or empty string. Let's take a second. What language is produced by this grammar?
Languages with n repetitions of AB.
N repetitions of AB, but the string BA cannot be produced by this grammar? Can it? No. It's a difficult one, the way I've written it, but I think it's a good exercise.
Well, this is the language AN to the BN starred.
AN to the BN star?
Something like that.
That I claim that could not produce BA, but it would fail to produce, that should still contain ABBA, right? No. ABBA? That might be produced by that. No, still, it's not. Is that correct? I don't think that's a good description of this language. But it might not be immediately incorrect. I don't think that's incorrect, but it's not a good description of this language, I think. Yes?
Would it be ANBN, ANBN? Or, no, not that.
I see, it's similar to what I think you guys are saying, where it's like AN, BN, AM, BM, something like that, right?
Yes, with more freedom.
This grammar should technically produce, though, A, B, B, right?
Yes.
Mm-hmm.
Okay, that doesn't fit the patterns.
Would it be A star, B star?
But every A must have a B. So A would be produced by A star, B star, but is not produced here. I feel good about how tough this one is, actually.
Would it be any string that start with an A and with a B and have the same amount of A and B's?
Starts with an A, ends with a B, and have the same amount of A's and B's. Can I come up with a counterexample? No, that's fine.
Where did you get these production rules?
Okay, I'll just tell you guys. I tricked you because this language is actually very commonly known, but it's never written with A and B. It's written with open parentheses and closed parentheses. Now, if I write it like that, what is the language produced by this grammar? Yeah.
I don't know how to phrase it, but every open parentheses has a closed parentheses, so it's a set of closed recursive sets of parentheses.
Yeah, maybe you understand, but you don't know what it's called.
Yeah.
Like, the word we're looking for is balanced. It's a string is balanced. So, for example, it does not produce this. It does not produce. It basically produces only balanced strings. By balanced, what we mean is it's like syntactically, you plug it into the calculator, it's not going to throw an error. It's grammatical in some sense, right? So it produces this. It produces, right? All those can be produced by this set of strings. And this is a sequence of balanced parentheses as well, right? The name for such a language is the Dick language. Named after, don't remember it, but that's probably his name. Strings of balanced parentheses. Again, something non-trivial here. We didn't actually talk about the Dick language when it comes to the theory of regular languages. Conjecture for me if the Dick language is regular or not. Yeah.
I want to say it's not,
Why?
because it grows both ways instead of only left to right.
Sure. Let's say you were in 1332 and you were asked for an automaton, not an automaton, a program to determine whether or not a string was balanced or not. What data structure would you use?
Stack.
Yeah, normally use a stack. Push in the open, pop out the close, something like this. That's probably not constant memory. So like intuitively, we can't do it like that. Now we could pump this language and prove it's not regular. We can do a simpler argument though. Assume to the contrary. That the Dick language is regular. Then, so would be the Dick language. Recall that the regular languages are closed under intersection. So if we intersect this with the regular language, it should also be regular. So we're going to intersect it with open star, closed star. That is a regular expression. Any number of opens followed by any number of closes. Let's take the intersection of that with the Dick language. What language will this be? Yeah.
It's going to be, open and close end, right?
Yes. Essentially, if it's in here, it's balanced. And if it's in here, every open must come before every close. So for example, that string would not be there because there's an open before a close, even though it's balanced. So what would you say are the strings in this language? In fact, if a string is balanced, it also must have an equal number of opens and closes. So this must have an equal number of opens and closes, and every open must come before a close. Right? What's our contradiction?
That's not regular.
Exactly. We prove that to be not regular by pumping. A to the n, B to the n, or open to the n, close to the n, same thing, right? So we prove that to not be regular. Contradiction. Now, how did we do this? We applied closure. Just to review real quick, assume to the contrary, the Dick language is regular. Since regular languages are close in an intersection, and that's regular, by assumption to the contrary. Since we know that the intersection of such languages is regular, this should be regular, but the intersection is a non-regular language. Contradiction. Yeah. Dick language not regular. Sometimes you don't need pumping, just throw some other stuff at it, you get the right answer. Yes?
So the intersection combines both rules and then only the same, I mean, for some reason, it's,
That's kind of the power of set theory, right? So if something is in the intersection, it must be in this and in this. So the elements of the intersection have to satisfy whatever both definitions happen to be. So it's an and of both. So it's a balanced parenthesis with an equal number of opens as closes, and this one restricts the fact that the opens must come before the closes. Okay? Speaking of logic, let's give a context-free grammar for the propositional calculus. Propositions, you know, look like this, right? P or Q and not R and not P. Something like that, right? We all know what the propositional calculus is. It's made up of what? Propositional variables, which can be assigned true or false, 1 or 0. And then it's made up of the 3 atomic operations, which are what? And, or, and not, right? You don't need implies because we have a conditional disjunctive equivalence, and we know that P implies Q is equivalent to not P or Q, and so on, right? So these are the 3 basic symbols. Now it turns out that the set of quote-unquote grammatical propositions can be produced by context-free grammar. That means we can create a grammar that produces the correct propositions without producing any of the incorrect ones. An incorrect proposition could be like P or, open, close, and, okay? That is a string, but it's not a, you look at it and you're like, obviously that's you give it to a calculator, it's gonna be like, that's wrong, you know? So we're gonna give a grammar for the propositions of propositional calculus. First problem, propositional letters, propositional variables. P, Q, R is what we usually use, S, T, A, B, sometimes I guess, X, Y, Z. Is too many letters. How many letters are there? It's not simply 26. In fact, you could have a proposition of not infinitely many, but a growing number of letters. You could have a proposition with more than 27 propositional variables. So we need some way to enumerate the propositional variables. So the first thing we're going to do is use unary strings. Question? No. Oh, okay, yeah. We're going to use unary strings. So instead of P, Q, R, we're going to use 1, 1, 1, 1, 1, 1, 1 to the 4th, and so on. Those are going to be our propositional variables, okay? So certainly each one is finite in length, but there's infinitely many of them. So that's the way we'll enumerate them. And let's even give me a context-free grammar to produce strings of this form. Let's call it N. N goes to what? Almost.
No, a 1N and 1.
Yes. Just by definition, we are not going to allow the empty string to be a proposition, because then otherwise that could be a valid propositional variable. Let's not do that, right? We want at least one propositional variable to be produced by such a non-terminal. Notice because this is not the empty string, it doesn't produce 1 star, but it in fact produces 1 star 1. So like 1 or more 1s instead of 0 or more 1s, right? Now, how can we create a set of productions for the propositional calculus, right? We have ands, ors, and nots. By the way, PEMDAS isn't real. I don't believe in PEMDAS. Please excuse my dear Aunt Sally. There's technically a PEMDAS for propositional calculus. Everything is a PEMDAS. You don't need PEMDAS. PEMDAS is like what they teach you, so if you just parenthesize your string correctly, you'll never need PEMDAS. So first of all, let's just pretend there's no PEMDAS, okay? The core idea to note is the same way that the grammar has a recursiveness to it, in the same way that substrings can be rewritten as other substrings. A proposition as a sequence of ands, ors, and nots and propositional variables contains within it smaller propositions and so on. So in fact, the definition of a proposition is actually it's called a well-formed formula. A well-formed formula is one, in fact, defined to be produced by this grammar that we're going to give you in a second. What grammar should I do? What are my productions from S? Yes.
Maybe the operations, so,
Okay.
or, and not.
Those, we will need those in our productions, but we want to make sure we don't produce or, for example.
So could it be, so every operation need a parentheses, right?
Yes.
So that would be parentheses, S and S.
That actually will also work, but I'll give you a shorthand. What he's saying is this. That works just fine, right? That as a beginning proposition. That allows you to parenthesize something.
Yes.
I'll tell you the shorter one,
Yeah.
which forces us to parenthesize in a way that we can ignore PEMDAS. Because this doesn't yet allow us to ignore PEMDAS.
This is what I, yeah, exactly.
We're almost done. One more thing.
And you also need the identify, the N, right?
Yeah, we need to somehow bottom out somewhere. So what we'll allow it to be is each one is going to be each of these can be a propositional variable, perhaps even the same propositional variable, right? N. Yeah. So notice you recursively apply S in such a way it does parenthesize. It parenthesizes itself out quite nicely, so you don't ever need to do PEMDAS. And then when you bottom out, you get your non-terminal N here, right? Yeah. Questions? By the way, every programming language, it is a difficult task. So what do you do when you compile a programming language? First, you run the syntax checker, right? It checks, did this guy actually write code that has all his semicolons and all his things are bounded, whatever, right? Types are declared. And then it actually does like non-trivial stuff. Type inference, loop shortening, whatever. Every programming language, technically, and this is not a very practical thing, but only a formality, can be defined by a context-free grammar. So in fact, usually the programming languages are defined by a context-free grammar. And then when the way the syntax checker works, which is like, how is this string that has been given to the compiler, is this actually a correct program? The way it determines that is actually just determining, can it be produced by the context-free grammar, which is defined to be the context-free grammar of the language, right? And then there are efficiency issues with that, like can this be fast or not, and so on, right? Things like this can occur. And then it turns out that even though they might be defined by context-free grammars, they might actually not be context-free and other issues like this. So they're very practical for defining languages as like, these are the strings that we want. These are the ones. So programming languages can be done this way, calculator arithmetic expressions, and so on. Question? Yes?
So would the parentheses being a terminal in this? Or
Yes,
part of
yes.
the production?
Good. What are our terminals? We have and or not. We have open and we have close, and then we have a one. So this is non-trivial, I should have said it, sorry about that. That's our set of terminals. Our set of non-terminals is simply gonna be S and N, right? What else? P, S, yeah, okay.
For the way you define, and you could generalize that onto, just letter identifiers, right?
So it's one of those things that like it's technical in what a proposition is. Does your definition allow for infinitely many propositional variables, but each one is described in finite length?
That's sticky.
Yes. So if you wanted, let's say, only 3 propositional variables, you could still do it. And then adjust the terminals appropriately. That would work, but this construction allows us to have arbitrarily many propositional variables. They're syntactically kind of odd, but it works out. So. Okay. Let's do a non-trivial one. So we have, suppose we know how to do a to the n, b to the n, but suppose I ask for a to the 2n, b to the n is a natural. Give me a context-free grammar that produces this language.
S goes to
Yeah. And? Yeah. Okay, so instead of ASB, here you can in fact kind of add basically a linear amount here. And every time you add a B on the right, you'll add two A's on the left. So you'll have 2n, A to the 2n, B to the n. Okay, what about, let's just make it harder, A to the 3n, and now you guys can do that one, B to the I, C to the n minus I comma n are natural numbers. And even let's say that n exceeds I. So we don't have a negative subtraction there. Right? This is a challenge one, yeah.
Would you need another non-terminal to represent this?
Well, this is the first one I think we really, well, that one actually had two non-terminals. But this one definitely needs two non-terminals. I don't know how to do it with fewer. So let's begin though. What's the core idea at least? We do need two non-terminals. Yes?
Non-terminal produce another non-terminal?
That's absolutely allowed, yeah.
I'll probably do AAA. N, is this where the,
Let's use R if you want. I like to use R.
and then,
I don't know why I used N there actually.
do we need another non-terminal or can it be done without another one?
I think it only needs two. Before we get too deep into what the productions are, what's the idea behind this? Like, what's the core idea?
You're producing a certain amount of A's, and you're producing a different amount of B's, and then you're producing a related amount of C's.
Yes. So they're related in some sense, right? So maybe I'll give you an incorrect grammar first. Yes.
Can I do triple A R and then R goes to B or C?
I think yeah. Let's talk about this one first then. So consider this one. Forget the R for now. Here's one core idea. Context-free grammars cannot be like subtractive. They cannot rewrite. They can like only write. So in a working string, if a terminal is produced, it's there until the end. It has to be there. Non-terminals can be produced around it, but the terminals are always there, right? So you can't actually like subtract off I from n here. But what you can do is notice that n minus I plus I is n. So this is in fact just n, and this is in fact 3n, right? So every 3 A's add a B or a C, right? There's a problem with this grammar though. Yeah.
That grammar makes it so that C's can come before B's.
Exactly. You could do BC, BC or something like this on the other side. So what we're going to do is we want to produce A's to C's, then we're going to switch gears. Think of the non-terminal use here kind of like a one-way door or even a transition. You're at some S. You produce recursive rules on S repeatedly. AAA, SC. You repeatedly do that some number of times. Then eventually you non-deterministically, because this production contains a non-terminal, you need to bottom out. So you need to go to R. You go to R. This is not a state diagram or anything, but mentally you can, similar mental model. Then you can recursively apply on S so many times. And then you bottom out. But notice that the way that S goes to R, and R stays at R can never go back to S. Kind of like a one-way door. So when you stop doing this production and you start doing this one, you basically are non-deterministically choosing, I'm going to stop C's and start doing B's. And that's when you switch from C, n minus I, to I. And now it still ensures that that relationship holds. Yes?
So wouldn't that relate the amount of A's and B's?
It relates the amount of A's to the sum of B's and C's. So here, yes, A's and C's are related. 3 A's for every C. And then 3 A's for every B. Because you have to go through R to bottom out, this is the number of, 3 times the number of A's is equal to the number of B's plus C's.
Is that also able to happen only because it's n minus I has to be 0 or greater?
Yeah. Okay, let's do one of my favorites. W hash x such that x contains the reversal of W as a substring. That's a difficult one, I think. Let's take a second to think about it. And let's suppose the alphabet is ABX. Excuse me, AB hash here. Before we try to think of productions and stuff, let's try to think of what does it mean for X to contain a substring. So if X contains a substring of the reversal of W, we know that then this kind of looks like W hash X. And then X though is some string, any possible string with the reversal of W in it. So what we could write is W hash, and then this would be like sigma star WR sigma star, right? Somewhere in there. But let's regroup that. We can write this as W hash sigma star WR. And then this is a sigma star out here. Right? You guys think we can produce this part, W and WR. Then we can produce this part. And then finally we can produce this last part. Right? So that's kind of how the construction of the grammar is going to go. So first off, we need a couple non-terminals for this one. S is going to go to, let's say, XY. And let Y be something that produces sigma star, right? So Y is going to go to what? Yes?
Any of so A, B hash, or sorry, A, Y, B, Y, hash Y?
Yeah, I made a mistake. Let's suppose there's only one hash per string. So let's say sigma prime is that, and then sigma is just AB. So when I say sigma, just so I don't have to erase sigma star here, sigma star is A's and B's only. Let's just make it that way. AY, BY, or empty string. Forget the hash on this. Notice each string contains, okay, another thing, X contains WR as a substring, but then W and X don't contain any hash. Okay, just to make it distinct there. So Y produces sigma star. Good. What should X produce?
The reverse, almost.
It's got to produce this whole thing, right? This part is done by Y. So recall, how do we do W and WR first? Again, outside in. Grammar is like a flower. You got to go from the outside parts first. How do we get the W with the WR?
AXA, BXB.
Okay. Now, normally where we would put the empty string to get WWR, we want this internal thing. So what is that? Do we need to create a new non-terminal though? That would actually work. So let's do two solutions. Let's go to Z, and then Z does what?
What do you call it? Hash Z.
Yes. And Z should produce what?
AZ, BZ, or empty string.
Yes. But I'll tell you a shortcut. Reuse the non-terminal. We don't have to do it twice. It's like a subroutine. It's like a program that does something for us. We can call the function twice. So this X produces the first half, which then, as the internal part, contains hash sigma star, and then we just append a sigma star at the end of the whole string entirely. Now, here's one of the reasons this is my favorite grammar. In algorithms, there are problems like studying like the longest palindromic subsequence and things like this. Like given a string, in a decision scenario, given a string, determining if the string accepts, contains as a substring a palindromic subsequence or like the reversal of another string usually is a little non-trivial. There's some creative algorithms around it. But really, this is probably, well, the context free grammar though is much simpler, simply by the power of non-determinism. When you're doing an algorithm that searches for some kind of reversal substring or something like this, you have to apply all these techniques, and that's because it's deterministic. But here, by non-determinism, you get something much faster. In the deterministic scenario, you're really like searching for a needle in a haystack. You're just kind of looking around and poking around. But non-deterministically, you get a much faster thing. It's not a real algorithm, but it's still the same description. Here's how the non-determinism works. Instead of searching for a needle in a haystack, what you do first is you place the needle, and then you non-deterministically choose all possible haystacks around that needle. Now, certainly you know the haystack contains the needle because you put it there, QED. Non-determinism. Questions on this grammar? See how much time we have. I got time. Let's do two more. So suppose I wanted a string like a to the n, b to the n, but I did not want to enforce that the a's come before the b's. I just want to enforce that there's an equal amount. Right. Give me a context-free grammar for that. Yes.
As we go to,
There's a couple wrong ones, but let's see.
so S goes to AS or AB, or sorry, BS.
So already here, if you apply this production, you have an A, and you've lost it, because you can't ensure that you always add a B. So I'll tell you this one. Recall the one for A to the n, B to the n. B to the n, it was like S goes to ASB, right? And that ensured two things. One, A's come before B's, and two, equal number of A's and B's. Because every time you added an A, you were forced to add a B. So let's relax the part where we want A's to come before B's, but let's keep the part where the A's equal to B's.
ASB, BSA, empty string.
That's almost right. ASB or BSA. Give me a string that's not produced by, or the empty string. There is a string not produced by this. Anything that begins and ends with the same letter. Counterexample.
AS, BS.
Yes. And that's actually correct, but the argument of correctness is a little more difficult. So I'm going to do a worse grammar that's more general. Make sure that every A has a B, and make sure of nothing else. Okay. Well, now what you said was it would actually work as well, AS, BS. But that certainly also works. Just fill every time you apply a production, the number of A's equal to the number of B's, and then every possible combination of substrings of that. So obviously it's gonna inductively preserve up. Right? A lot of things about context-free grammars as well can be proven by induction. Right? If you wanted to prove, for example, any string produced by this grammar has an equal number of A's and B's, assume K productions, obviously it works. The next production is gonna add one A and one B, right? Okay, that's it. Now suppose I wanted something worse. W is in sigma star, such that the number of A's of W plus the number of B's of W is equal to the number of C's of W plus the number of D's of W, such that sigma is, let sigma here be A, comma B, comma C, comma D. Okay. Give me a grammar for that one. Doesn't have to be bad, a good grammar necessarily, but. Yes.
S goes to ASC or ASD.
Yes. Yeah. So before we get too intimate with the actual productions, let's describe what's going to happen. You're going to choose, every time you put an A, you're going to make sure you put a C or a D. And every time you put a B, you're going to make sure you put a C or a D. So following a similar pattern, it's going to be S, A, S, C, S, or S, A, S, D, S, or, we're not done though.
SBSCS.
S, B, S, C, S, or S.
ESDS.
We're also not done, we have more.
Empty string or
Well, versus. A's before C's here, but we need C's before A's perhaps. Or empty string, okay. That's long, that's difficult grammar. Can you do it easier? Can you give me a shorter grammar for this? Leverage the power of non-determinism here.
Can we use a non-terminal for this?
Yes. Use more non-terminal, that's okay.
S goes to SX SYS
Yeah.
or SYS XS, and then set X to A or B, and then Y to C or D.
Exactly. Let's describe the idea. You have to balance an equation. So make sure the number of things on the left equals the number of things on the right. Okay, fine. But instead of matching every possible combination of things on the left to things on the right, what you're going to do is you leverage non-determinism. So you match the number of things on the left to be the number of things on the right, and then non-deterministically choose which thing on the left it is and which thing on the right it is. So S is going to go to S, X, S, Y, S, or S, Y, S, X, S. And then X is going to just be the things on the left. And then Y is going to be the things on the right. Oops. That's right.
I guess also had empty string.
Do I need an empty string? Yes, here. Questions? All right, let's take a break.